Hello, kidlets. Today we're going to be talking about some basic stellar properties and how we measure stars and determine their distance. So if you remember last semester, we talked about parallax, and we talked about how we use, I'm going to expand on this picture, we use the Earth and the orbit of Earth as our baseline, and we use that 6 months apart because remember the distance between the Sun and the Earth is 1 AU, which is about 150 million kilometers. And we need a larger baseline than that because it's really not that big if we think about stellar space. And then we measure that angle, the angle here on this side, and then 6 months later we measure the angle here on this side. And from those angles, then our unknown is the distance, and we can just use triangulation to be able to measure that. So we talked about that last semester, and the reason we have to do it 2 months apart is to be able to actually see a distance because we're so close to the sun. Or because we're so close to our star, so that then we can determine a distance out here. So if we look at a star that we see here, and we look at it from this position, we could get an angle like this. And if we look at it here, so say this is January, over here being July, then we get this. So we can see an apparent shift, and then astronomers can measure that shift, and this is what the parallax angle is the difference between the two. So, and we can think about these model distances. We think about us and the sun having a distance of 1 AU, and if we gave the sun as a marble and the Earth as a grain of sand that was a meteor away, that would make our nearest star 270 kilometers away. And the nearest star to the sun, Proxima Centauri, is a member of the Centauri complex, which is really 300,000 AU away. So in our model distance, it would be 270 kilometers. So here is just an overview of the 30 stars close to us. So all of these are our stellar neighborhood, which were all probably in the same solar nebula as our sun. They're all about the same size, about the same luminosity, and about the same age. So they were probably all created in the same solar nebula. So proper motion, just real quick, this is the way that a star actually moves. So we move through space, all stars rotate, all stars actually move, so they have a radial motion in relation to us, and then they have a transverse motion that's perpendicular to us. And the one that has the greatest proper motion is Barnard's star. So if we look here, there's the star, and 22 years later, it's here. And one of the reasons that we probably see the greatest proper motion is because it's not very far from us. So next is luminosity and brightness measurements. So pretty intuitive, but the more distant a light source is, the fainter it appears. But it could be a very bright star that just happens to be really far away. So to us, it would appear very, very faint. Because brightness is also relative. So we have intrinsic brightness or absolute magnitude, and then we also have apparent brightness. So if we look here at star A is obviously bigger than star B, but they could appear in the night sky as the same luminosity because of their difference in diameters, but also the difference in their distances. So intrinsic brightness would be the absolute property of the star, not based on distance. So here we have a real example of that in my favorite constellation of Orion. So here you can see the belt stars, there's Betelgeuse, the red shoulder, and Rigel, the blue foot. So red giant star, blue giant star. So Rigel appears to be bigger and brighter, but it's actually a much greater distance away. So if they were put at the same level, then Rigel would appear to our eyes as being a much more luminous star in the sky. So here again, looking in the Orion constellation, so there's drastic differences in the distances between these stars. So there's over 1,000 light years between Earth and the most distant star in Orion, but yet we can see them all. So luminosity is a measure of the star's total energy. The total energy radiated by the star, and that's intrinsic because it's independent of distance, whereas the apparent brightness, opposite of absolute brightness, the apparent brightness is how bright a star appears when viewed from Earth. And this is distance dependent. So that's the main difference here, is that your luminosity is intrinsic. It's the actual energy of the star independent of distance. And apparent brightness is how it appears. So, and then the apparent brightness, just like we said, is inversely proportional to our distance squared. And the luminosity is based on the internal properties of the star, and here is the magnitude scale.